Hi guys, so we have our last question about this subject. So right in all the other questions we actually do the same thing, and we're going to do it the same here. So we asking what is the total charge, and we always took the level up of the question. So right now the question is for a solid sphere. Okay, so before we had a shallow sphere, we talked about only the mirrors of this thing, but now I want to talk about a general case when I also have some charge distribution inside the sphere. So the charge density, it's going to be really simple this time. It's going to be just a constant, okay? But we still need to figure out how to find the total charge. And we said before, the total charge, which sign is Q total, is made of its parts, right? We need to sum all the small chunks of charge that we have in the sphere, which I know it's the same. Every piece is distributed the same. This is units of Coulomb per meter cube, right? And I need to find. So let's draw the sphere. So sphere is looking like this, right? X, Y, and Z. And we know already that using Cartesian coordinates for a sphere, it's not going to be a perfect match, okay? Better match going to be use the spherical coordinates, which is kind of improvement of the polar. So what we actually can use is, we already talked about that when we talk about the shell. We have two angles, right? If I want to describe a piece, look, this is a piece, and if I want to use this piece and build a sphere, it's not going to be enough to use stickers, right? This is a sticker, right? So we're going to see how we can improve this one. We want a Lego brick, right, that we can build on. So, but let's talk about this. It's a good rehearsal. So we talked about that we need two angles to describe the shell itself, right? We need the angle phi, that's starting from the top down below. I think about like a sniper shooter, from down up. So this is actually the angle phi, and this one is the angle, this is theta, and this is usually phi. Yeah, they're confusing it sometimes. You need to be aware of that, okay? So we said that this piece is actually having this distance and this distance, and this distance is really easy. It's just a change of d theta, right? But note that now the piece can be not on the other shell, but also inside. So I don't know what radius distance from the center it is. So this is going to be multiplied by r, a general radius from the center, right? Yes? Let's do it like this. We're going to actually extend this piece to be a Lego brick, right? So this part is actually r d theta. Okay? A general r. Right? Perfect. And now I want to talk about what is this thing, the size of this thing. This is an area, right? And this is something that I extended to be a volume, right? This is a dV. It's the reason we have here rho. Rho talking about volumes. Perfect. So this thing is actually d phi, but it's not multiplied by r, because we're talking about a really smaller circle. You see, it's not, you have this circle and you have this circle, the most big one, right? So this one is actually, if this is the distance r, this one end up to be r sinus theta. R sinus theta. It's a smaller r, and it's really reached the maximum when it's over here, when the chunk is over here, right? But if I'm all the way here, the chunk is really small, even 0. Okay? And you can see it. Oh, I didn't brought it. I brought a globe. Okay? So you can actually see on the globe itself that these pieces that divide the world, you see it? That the areas here are really huge, and the areas here on the north and the south are really small. And that is for the same reason. Okay? So that's the concept with that. Okay? I told you I'm a really visual person. Yeah? Okay, good. So I want to ask you the last question. To describe what is the volume of this creature, we need to have this area, which we found. But how are we going to call this distance? I want to remind you, this is the distance from the origin. Okay, so this is the radial direction. So this is like how far I am from the middle. Okay, I'm a piece inside. If this is a 3D, right, and I cut it, you can see through it. Piece can be in the middle, can be here, can be here, can be here, right? So this distance is R. So how am I going to call this distance? If this R, it's a small change in R, so it's dr. Okay, so this is my full piece. This and this dr. Let's do it in a better drawing. So my piece is looking like this, right? This is my piece, right? This is d phi r sinus theta. This is d theta multiplied by r, and this is this distance. This one is dr, like this. Okay, got it? You understand? And with this I can actually build the block. Okay, so let's write the total. It's equal to dq, which is rho naught, right? Multiplied by dv. All of this creature is dv. Is everybody multiplies by each other, okay? So it's dr, perfect. It's d phi r sinus theta, right? And it's also this it's also r d theta, right? The last piece, right? And I wanted to note something. I gave you a really, really easy charge distribution. What the charge distribution is?
Constant.
It's a constant. So if I can take this constant out of the integral, right? Constant, and of course I have here 3 integrals, right? So I have here actually 3 integrals, right? What I end up with, this is rho naught. This is the integral that sum up actually small pieces of volumes, right? And the boundaries should give me at the end all the solid sphere. So instead of calculating this integral, I already know the results, right? What is the answer of this thing? It's going to be the volume of sphere. Because if I'm going to take a small pieces of sphere and build a sphere with the boundaries, I'm going to end up with the sphere. Okay? So this is actually the shortcut to how to solve this question. And this is going to end up to be rho naught multiplied by 4 pi r to the third divided by 3. Okay? This is a volume of a solid sphere, which I want you to remember. It's really important. Okay, guys? Okay? Perfect. And this idea can be used in many other examples. I'm going to send you another question, but it's always going to happen. Let's go. You can go here, cameraman. So if we're actually going to have some charge distribution that look like this, just the constants, okay, it's going to be, okay, the total charge, this is a density, right? Charge density, and this is going to be total charge, Q total. So this thing is going to be just multiplied by the length. And this thing going to be just multiplied by all the area that you have. And here it's going to be multiplied by all the volume that you have. Okay? So here the solution going to be really simple. And let me tell you some secret. Most of the time, things spread evenly spaced. Even charge, okay? Sometimes not. This is the interesting cases. But most of the things in nature actually behave that way. It's really nice and easy, okay? So that's what I want you to know, okay? Perfect, guys. This was the class. Next class, we're going to talk about forces, okay? So I'm going to see you next week. Good luck. Hope that the video helped you. Put like if you like, and if you have any question down below in the comments. See you next time.